So, question 14, if you open up the booklet, that's where we finished up last time. So I reckon we'll spend probably 20 minutes, half an hour doing these. And then I can come around and just see how you guys are all doing and see if you have any questions you'd like to go through either together or individually. So question 14, does everyone have their booklet? Excellent, let's read it. We have extrasensory perception, ESP, is defined as the reception of information without the use of recognised physical senses such as sight or hearing. One test involves Zener cards. A set of 25 Zener cards contains 5 of each of the cards illustrated below. In this test, an administrator randomly selects one card from the set of 25 cards and the card concealed from the test subject who attempts to correctly identify the symbol. The test administrator records whether or not the test subject correctly identifies the symbol. So explain why the test subject's attempt to correctly identify which of the 5 symbols is printed on a selected card constitutes a Binomial trial. So for part A, what are the requisite conditions for a Binomial trial? We have one trial, 2 possible outcomes. Okay? And so because it satisfies both of those, it's a Binomial distribution. The outcomes are either correct or not correct guess, and we're only performing it once. Okay, to complete the test, the process described above is undertaken 25 times, with cards being returned to the set between each attempt. So 25 cards in the deck, and there's 5 of each symbol, isn't there? So 5 cards of the same kind. Let X represent the number of correct identifications out of 25 attempts, where the test subject is identifying symbols at random, with the probability of correct identification P equals 0.2. What is the probability that the test subject makes exactly 5 correct identifications? Okay, so 2 ways we can do this. Let's just talk about the distribution of X first. It's binomial. The probability of success is 0.2, and there are 25 trials. You're doing it 25 times. Now this question's here saying exactly 5 outcomes, so that's the probability that this variable is 5. So 2 ways we can do that. We can do a Bcd calculation, where we have X and P, so 5, 25 and 0.25. Okay, or you can think about it in terms of the binomial distribution formula, which is C, we have 25 and 5. The probability of success to the number of successes, and the probability of failure to the number of failures. Okay, so either of these is going to generate the correct solution. Let's go ahead and calculate that now. Distribution binomial Bcd 525.2 0.1960, so 0.196. So what that means is the probability of getting 5 correct at random is 0.196. Okay. Part 2, no more than 7 correct identifications. So the way we think about these, right, so that's B part 2, isn't it? B part 1, B part 2. If we can have, we could get, 1 correct, you could get 2, 3, 4, 5, 6, 7, 8. You could get all of them correct, okay? We're saying no more than 7, okay? So 7 or less, all right? Because 6 could be 5, could be 4. So that's a Bcd calculation, where the lower boundary is 0. The upper boundary is 7. So Bcd, lower boundary, upper boundary. Number of trials is 25, and probability of success 0.2. So that's the calculation we're doing there. That is the probability of the variable being less than or equal to 7. So that's going to be distribution binomial Bcd. The lower boundary is 0, upper boundary 7. 0.8908 so 0.891. So we have an 89.1% chance of getting 7 or less correct. Okay. Part C. In the context of the problem, write a probability statement that's equivalent to this one. So this is the statement here. I can do that here. C part 1. We've got C 825, 0.2 to the power of 8, 0.8 to the power of 7. Okay, so we know this binomial distribution formula. Okay, number of trials, number of successes, probability of success to the number of successes, probability of failure to the number of failures. So this is the probability of getting exactly 8 correct. All right, and so that's what it wants, is a statement about what it means. What does it mean? Probability of getting 8 correct identifications. Okay. Then in part 2 it says, what about if we do this one takeaway, C025, 0.2 to the power of 0, 0.8 to the power of 25. Okay, what is, and that's 0.996. All right, so one take away this event. Well, what is this event here? This is the probability of 0 successes. Okay, so if you think of all the possible events, you could have 0 successes, you could have 1, you could have 2, all the way up to 25. So if we eliminate this event, it means we're including every other possible event. So this is the probability of at least 1 success. Okay? Yep, probability of at least 1 success. One correct identification. Use the language they're using. Now, stop me at any stage. I think the stuff we've done so far is pretty similar to the stuff that you've seen in some of our tests.
Could you go through that question again?
Just this part?
Yes, please.
Yep. So, so it's saying, what does it mean? What's it? Write a probability statement for it. Okay. So we know this is binomial distribution formula. This is the number of trials. This is the number of successes. So this event here is the probability of getting 0 successes. Okay. And so if we do one take away that event, well, this is the sum of all probable events. And if we're eliminating the event where there's 0 successes, it means we're allowing for every other event. What are all the other events? Well, 0 is one of them. Every other event is larger than 1. Yep.
Yep.
Excellent.
Thank you.
No worries. Okay, so to be successful in this test, the test subject must make at least k correct identifications, where k is chosen so that the chance of being successful by random identifications in symbols is less than 2.5%. Calculate k star, that is the minimum value of k. Support your answer with probability calculations correct to 4 significant figures. So, what we can see here from this statement is that the probability of getting less than 7 correct is 0.891. Okay? So the probability of getting less than 7, less than or equal to 7, is 0.891. So I want you to think about it like this. That means the probability of getting 8 or more. So if we've got those events, we've got 6, 7, 8, 9, 10, 11, 12. And we're saying, how many do they need to guess correctly such that the probability of it being at random, that they would to get correct identifications, would be less than 2.5%. Okay? If we're talking about less than 7, all right, so that's that event there. That's just, the inverse of that is more, 8 or more, isn't it? So the probability of x being larger than 8 is going to be 1 take away this, 0.891, which will be 9, 911. 0.109. Okay, so the probability of getting 8 or more correct is 0.109. Okay, so 8, it's not high enough. what about the probability of getting 9 or more correct? Okay, so we're going to have to do this calculation. That's going to be BCD, our lower boundary is 9, upper boundary 25, 25 trials, and the probability of success is 0.2. So 9, 25, 25.2. That's a 7, 6, 8. Okay, but they've said 2.5%. So this is 4.6%. So we're not quite there. What happens if we go 10? The probability of x being larger than or equal to 10. So it's the same calculation. The only thing we're changing is the lower boundary. 10, 25, 25, 0.2. Okay, and when we do this, we get 0.0173. And that is less than 2.5%, isn't it? Okay. So let's try and explain all that in the context of the problem. I've performed the calculations there for it, but they're saying we want it set up, okay, we want it set up such that there's this number of cards they need to guess K, such that the probability of it being, of them getting it correct randomly is less than 2.5%. So what we've seen is if you're guessing, if you guess 8 or more cards correct at random, the probability of that occurring is 10%. Okay? The probability of getting 9 or more cards at random is 4.68%. And when we have the probability of getting 10 or more cards at random, it is 1.73%, which is less than the 2.5% that they're asking for. Okay, so our value of K is 10. That's how many questions they need to guess correctly. So let's answer that, therefore K is 10. All right. Kyle, do you have a book?
No.
No. So we're on question 14, 15, 16. Does anyone else not have a book that holding? Where's yours?
What do you mean?
Last time.
Last time?
Yeah, it's the same book.
What do you mean last time? I didn't come to the last church.
Yes, he did.
No, I didn't.
We'll talk about it later. I reckon you did. Okay, students at high school watched a television program investigating ESP. One student, Ari, undertook an ESP test using Xenocards and made K correct identifications, where K is the value you calculate in part B. So that means Ari made 10 correct identifications. Based on the information in part D, what can be said about Ari's claim? All right, so it seems very unlikely, based on our calculation here, okay, the probability of getting 10 or more correct at random is 0.0173. So it seems, based on our calculation, very unlikely to guess them at random. So perhaps Ari is justified in her claim, because it seems unlikely based on our calculation. So let's write that. It is very unlikely to guess 10 or more correct at random. So Ari's claim may be justified. So whether you believe in ESP or not, leave that at the door. Okay. Here we're just looking at the mathematical significance of it. It does seem quite low, so perhaps it's justified. Okay, but then we're going to do some further maths here to challenge that idea. F. If 624 students undertook an ESP test using Xenocards and were identifying symbols at random, what is the probability that one or more of these students would make at least K correct identifications? So now we've got every student in the high school doing it. All right, so that's 624 students. 624 students in high school doing this experiment. And we're saying, what is the probability that at least one of them is going to get 10 or more correct? Okay? Now we saw before the probability of getting at least 10. Okay, the probability of getting at least 10, 0.0173. Now we're saying, what is the probability of one student? So what's the best way for us to communicate that? Let's think about it like this. The Bcd calculation, we're saying at least one student out of 624, okay, at least one student out of lower boundary, upper boundary, number of trials. And what is the probability of a single student getting 10 or more correct at random? That's this probability that we calculated here, isn't it? 0.0173. Okay, so the significance of this calculation is we're saying, this seems very low, right? It's a very low probability of that occurring, but we're performing that experiment 624 times, okay? So let's perform this calculation and then come up with some cool answer here. So lower boundary 1, upper boundary 624, 624 and 0.0173. Oh, look at that, I've got 0.99998. Okay? What does that mean? Okay, it means even though it's very unlikely for a single person to do it, when we repeat that experiment 624 times, it's almost certain to happen that at least one person will get 10 or more identifications correct. So let's write that. Sorry, we don't need to write that yet. So this is our answer to part F. So that's the probability of it. So then part G. The principal of the school suggests Ari was identifying symbols at random and hence does not possess ESP. How does your answer to part F support the principal's suggestion? And that's exactly what we're observing. So how are we going to write that? So even though I think that's a pretty good way of saying it. Even though the probability of a single student choosing 10 or more at random is very low, it's repeated 624 times, which means it's almost certain that it's going to occur once. All right? So it's like having an 1,000-sided dice, right? You know, on one of those sides is a 1. You roll it enough times, eventually a 1 is going to come up. Cool. Any questions about that? Okay, now most of this question is pretty straightforward, but there is one tricky part. So we have Wacky Quackers is a popular amusement game in Australia. In the game, a player selects from a very large number of identical looking plastic ducks that are floating in a pool of water. Each duck has the number 1, 2, 5 or 10 printed on its base. The numbers cannot be seen by the player when making their selection. The number that is printed on the selected duck will be used to determine the prize. Okay, so you've seen this game at the show that there's the ducks floating, you get a fishing rod, you have to try and get the ducks out. The numbers underneath. And we have this probability distribution here. So as you can see, most of the ducks have a 1 on the bottom. In fact, 50% do. We have 20% with a 2, 20% with a 5, and 10% with a 10. That's our probability distribution. Calculate the mean, and it does say beneath calculate the standard deviation. Okay, so if you wanted to, you can write out a manual calculation for it, you can do it. But I'm just thinking, in the interest of time, let's just put it as a table in our calculator, because we know the standard deviation can be a little bit more tedious. So I'm just going to go, 1, 2, 5, and 10. in my first list. And in the second list, 0.5, 0.2, 0.2 and 0.1. Now we need to make sure here, guys, that our calculator's on the right setting, don't we? So that means when we go into our settings, it needs to say list 1 against list 2. So first variance X list is list 1, first variance frequency is list 2. Okay, so that's the first setting. First variance X list, and then first variance frequency. Okay, if we do that, then it's going to generate the right solution for us. So I've got a mean of 2.9, and I've got a standard deviation of 2.808, which is 2.81.
What did you do just there?
I'm just checking the settings in my calculator to make sure it says list 1, list 2.
Yep.
So we do that when we have two rows of data, 2 columns of data. All right, so that's the first page, solve the 4 marks there, just for doing that.
How do we get 2 marks out of each of those?
For getting the answer. Yeah. You don't need to show any work. So what is the probability that a player, sorry, I should read the whole thing here. A player can pay $10 and randomly select 3 ducks. This player wins a prize that has dollar value, some number, equal to the sum of the number printed on the back of the 3 ducks, okay? So, you know, if you pick out 3 ducks and you got a 1, a 2, and a 5, then you would get $8, okay? If you picked out 3 10s, then you're going to get $30, all right? So what is the probability that a player who randomly selects 3 ducks will win a prize that has a value of $30? Okay, so in order to get $30, you need to get the 10 3 times in a row. What is the probability of getting a 10? It's 0.1. So 0.1 times 0.1 times 0.1. Okay. Now this next part is probably the trickiest part in this question. Okay. What is the probability that a player who randomly selects 3 ducks will win a prize that has a value of at least $5? Okay. So if you're randomly selecting 3 ducks, all right, you can think of all the possible events that could occur. Okay. You could get a 10, and then a 5, in which case you've got more than $5. You could get a 10, a 5, and then a 10. Okay, you could get a 5, a 1, and then a 1. Like, there are so many instances of where you can get $5 or more. That's what it's asking you. That has a value of at least $5. Okay, so there's a better way to think about it. All right, and that's the tricky part to this question. We can say, if we're thinking about the probability of it being more than 5, okay, is equal to 1 take the probability of it being less than 4. And this is a much easier calculation for us to perform. Okay? Less than or equal to 4. Okay? Because let's think about the way that you could get $4. Okay? Or you could have less than $4. Alright? That would be if you got 1, 1, and 1. Okay, so let's list the events. You could get 1, 1, 1. It would be if you got 2, 1, 1. If you got 1, 2, 1. And if you got 1, 1, 2. Okay? They're all the same event. That's all getting 4. Okay, that's getting $4. And this is the only way you can get $3. But they're the only events that are $5 or less. Okay? So what's the probability of them occurring? Well, this is 0.5 times 0.5 times 0.5. Okay, that's this event. And then this event here, so you could calculate each separately. You know, it's 0.2 times 0.5 times 0.5. And in fact, all of them have the same probability, and there's 3 ways it can happen. Okay? So I'm going to finish calculating these. 0.5 to the power of 3, and 0.3 times 0.2. That's 0.125, and then 0.3 times 0.2 times 0.5 times 0.5, 0.15. What's that? 275. Okay, so what that means is the probability of getting $4 or less is 0.275. And so the probability of getting 5 or more is going to be 1 take away this probability. So what's that? 0.825. 725. All right. Everyone see that?
So there's not 3 different ways the 1, 1, 1 can happen, is there?
Yeah, there's only one possible way that can happen.
Sure.
Yeah, because here the order isn't going to matter, whereas here it does, because you have different events occurring. Whereas here, because there's only one event occurring, there's only one order. There's only one possible way it can happen. Yeah. So let's just recap that quickly. What do we do? Here, the probability of more than 5 or more. And we've said, well, there's infinite ways that can happen. That's going to be a really nasty calculation to calculate all of them. So how can we think about it differently? Well, what's the probability of it being, what's the inverse? 1 take the probability being less than 4. There's not many calculations involved there. You could get 3 ducks, or $3 worth of ducks, or you could get $4 worth of ducks, and they're the only ways that can occur. All right. Okay, so moving on. C part 1. Let the discrete random variable S3 represent the sum of the numbers printed on 3 randomly selected ducks. Calculate the mean of S3. Okay, so the mean of S3 is equal to n times the mean of x, isn't it? So it's equal to 3 times 2.9. And the standard deviation, so 8.7. Okay, so that's part 1, C part 1. And then C part 2. So most of this question, we should be able to get most of the marks in this question. The standard deviation of S3, well that's this, now for the sum, it's the square root of n times the standard deviation of x. All right, you'll have these things written on your formula sheet, so you'll be right with that. So that's the square root of 3 times 2.81. And we've got 4.867. 4.87. Okay, always rounding to 3 significant figures unless it states otherwise. Okay, excellent. So alternatively, a player can pay $16 and randomly select 5 ducks. This player wins a prize that has a dollar value equal to the sum of the numbers printed on the 5 ducks. Calculate the expected value of the sum of numbers printed on the 5 randomly selected ducks. Okay? So let's just explain that. This is what we expect you to get on average if you play the game once. Okay? We expect you to get $2.9. Alright? This is what we expect you to get if you play the game 3 times. If you pull 3 ducks out, on average you should get 8.7. Now they're saying, what's going to be the average if you play it 5 times? Well, that's the mean of S5. Okay? So that's going to be 5 times the mean of x. So 5 times 2.9, what's that, 12? 14.5. Okay, so if you pull 5 ducks out, it's expected that you get $14.50. Okay, using your answers to C and D, determine which one of the 2 options will be more profitable for the owner of wacky ducks in the long run. So let's look at the options they have there. You can pay $16 $16, and that's when you're playing the game 5 times. Okay, you get 5 times, and if you play that, right, on average you're going to get $14.50. Okay, or the customer gets $14.50. So how much profit is the owner making? The owner, so profit is $1.50 in this circumstance. All right. The other option is to play it 3 times for $10. Where did we see that? At the top of that page. A player can pay $10 and randomly select 3 ducks. So $10 for 3 times, three goes. And if you're playing it 3 times, then you can expect to get $8.70 on average. That's what the player is going to get, $8.70. So how much profit does that leave the owner with? $1.30. Okay. So which one of these options is better for the owner? This one, where they get to pick 5 ducks because he's making more profit. Okay. All right. Through the boards, you're going to need these boards to be this one. Okay, consider the function 4x e to the minus x. The graph is below. Determine the coordinates of the stationary point. Give your answer correct to 3 decimal places. So I'm going, let's graph that and let's g-solve that point. So I'm going to sketch the graph up here. You guys bring it up on your calculator while I'm doing this. We're going to be doing a bit on our calculator with this one, I reckon. Okay, so then part A, stationary point, just says state the coordinates of it. So we can see x is 1, and then the y value is going to be 4e to the negative 1, but it says correct to 3 decimal places, doesn't it? Make sure you sketch it over the same B window they give us. Okay, that's a hot tip. So 0 to 5 and 0 to 2. G-solve max. Okay, the stationary point is 1. Now let's read that carefully. It says correct to 3 decimal places. So that means we're going to write 4 decimal places and round the 4th decimal place. 1.4715. Okay, there's 4 decimal places, and we round that number 472. Okay, part B. Determine the coordinates of the inflection point on the graph. Okay, so there's an inflection point here somewhere. They want us to find the coordinates, all right? It's only worth 2 marks, all right? We're not going to go through some differentiation of it. What is it, 4x e to the minus x? Okay, we're not going to differentiate it and find the, using the product rule and then draw the sign diagram and make it equal to 0. We could do it like that, but it's just going to take way too long. Let's just use our calculator. All it says is determine the coordinates. Okay, I'll give you your answer correct. So we have a point of inflection here somewhere. Now what we should remember is if we have f of x, the point of inflection on f of x corresponds with a turning point. Okay, so that's a maximum or minimum on f dash of x, and it's a root on the second derivative. Okay, so there's 2 ways we can do this. What we should do is we should go back to our graph menu and we should graph either the derivative function or the second derivative function. Now one thing you should have noticed as well is that when you graph the second derivative, it does take a little bit longer because there's more computing involved. All right, so just in the interest of time, I'm going to I'm going to graph the derivative, all right, just by going find d on dx. And I'm going to get the x value of the max, okay? Not the y value, because we need the y value on this function, on the original function, okay? So I'm going to graph it. I'm going to go option calc d on dx of y1. We don't need the graph of the first derivative. We're going to need to change our v window as well. Okay, and what we can see is we have a minimum, like the derivative is going like that. We have a minimum. Let's g-solve the coordinates of the minimum. The x value is 2.006, so 2. All right, and so then we need the y value on the original function when x is 2. So I'm going to go back to my graph, sketch the original function, and I'm going to say, yo, what's the y value when x is 2? 1.0826. Okay, so 3 decimal places, that's going to be 1.083.
Does that mean you'd put it as 2.006 as well?
No,
It's 3 decimal
there was
places.
like 7 zeros and then a 6.
Oh, right.
Yeah. Oh, sorry, I hear what you're saying. Yeah, so it says give your answer correct to 3 decimal places. So I think you're correct that we should express that as a decimal. 2.000, and this is 1.000. Yeah, good pickup.
Mr. Rose, I'm confused with that one.
Yeah. I can go through it up here, I suppose. Should I do that?
Well, yeah.
Yep. Bring up the calculator there. So we got Vivi. What's the code there for me, guys?
0996.
Got calculator open. All right, there we go. So in graph, okay, you get the function 4x e to the minus x. Whoop. Ah, it's clunky using it on the computer. E to the minus x. Which one's in that? I'll just type it in, minus x. Okay, and I've already got the graph of the derivative there, so I'll turn that on. Okay, so hopefully we followed along with that. We've got the original function. Here's the graph of the derivative. Okay, and so I'm just interested in the derivative. I'll just check my V window here. That's pretty good. It's suitable. What we can see is we've got a minimum. So if I go g solve min, okay, that's giving up that x value for me. Now I only want the x value, okay, because then I'm going to go back to the original function. I'll just unselect the second derivative. And I want to know what is the y value when x is 2. Okay, so I got this x value here. What's the y value? All right, so that's how I'm generating that. And why do I know that's the case? Well, point of inflection on f of x, there's no way we can just g-solve a point of inflection. It requires a bit of a knowledge of calculus. The point of inflection occurs at a turning point on the first derivative. That's the x value of the point of inflection. We want the coordinates of the point of inflection, so we've got the x value, but we need the corresponding y value. All right, is that okay? Yeah, thank you. Excellent. All right, here we have the graph of f of x is shown below, and a tangent to this graph at x is 3 is drawn. On the graph, draw a tangent that has a greater y-intercept. So when you're thinking of a tangent, right, so the tangent's like here or something like that. I'll just draw what they've got. Their tangent's like this, okay? And they're saying draw a tangent that has a y-intercept that's larger. So any tangent with a y-intercept that's further up here. Well, that could be anywhere along here. What you can see is if I draw this tangent, okay, that's going to be significantly larger. So draw a tangent to the curve using the ruler. That's just going to have a y value larger than 3. Just needs to be approximate. Okay, let's look at part C. Show that the tangent to the graph at x equals a has the equation, and then we've got a nasty equation there, okay? So what that means is find the tangent at x is a. So we know to find the equation of a tangent, we need two things. We need the point of contact and the slope, okay? So for the point of contact, we're talking about the x value a. The x value is a, some number a, could be any number. And the y value, what's the function? The function is 4x e to the minus x. Yep. So the y value is going to be 4a e to the minus a. So we've got the point of contact. Okay, halfway there. Then we need the slope. So how are we going to find the slope? If this is the function, the way we're going to find the slope is we find the derivative, and then we put the x value into the derivative function. How do we differentiate this? 4x e to the minus x. We have to use the product rule. We have one function times another. So let's go ahead and find the slope. We've got u is 4x, u dash is 4, v is e to the minus x, and v dash is minus e to the minus x. Okay. Now we can simplify this a bit, and you could simplify it at any stage, but I'm just looking at, I might just leave it for now. No, we'll simplify it now. If we go, what's common to both of these? 4 and e to the minus x, isn't it? And so then what are we left with? In brackets, it's going to be 1 take x. Okay? If you expand this, then this is what you're going to get. And the reason I've done that is I'm looking at what it wants us to get, okay? And I can see it's like 4 times 1 take a. So, you know, here's 1 take x. And we're talking about the slope when x equals a, okay? So remember, this is the slope function for any value of x. You put x is 2 in there, it's going to tell you how steep it is at x is 2. We're interested in the tangent at a. So when x is a, what's dy on dx? It's going to be 4e to the minus a times 1 take a. Okay, now let's think about a tangent. What is a tangent? It's the equation of a line, y equals mx plus c. We've got m, okay? That's our value of m. That's our slope at x is a. So we're going to take that and put that there. And you can see we're getting pretty close to what they want us to have. And we can write it in the order that they have it expressed as well, which is 4 times 1 take a e to the minus a. So that's the value of m. So we have mx plus c. How do we find c? Well, this is when we plug the point of contact in. We have when x is a, y is 4a e to the minus a. So when we put the value of a into where x is here, we're going to have the, that's correct. When we put the value of a in, we're going to have y is 4a e to the minus a. So let's do that. 4a e to the minus a. So what have I done? I substituted a where the x is, and I substituted 4a e to the minus a where the y is. Okay, we're looking to get c by itself. Now what have they expressed c as? 4a squared e to the minus a. Okay, so maybe it was a bit silly to simplify it over there, but nonetheless it's going to work, it will come out in the wash. Okay, so we want to get c by itself, so that means we're going to move this over to this side. So over here I'm going to have 4a e to the minus a, take 4 times 1 take a, e to the minus a times a. Okay, all I've done in that step is move that over to the other side. and we need to collect them. Like let's look at where we're aiming to get to. We're aiming to get to this. 4 times 1 take a e to the minus a x plus 4a squared e to the minus a. So we've already got that part. Okay, that's what we got. We can see that here. Okay, that we've got the slope. All right. We're trying to get this for the value of c. c is 4a squared e to the minus a. So if we want to collect them to look something like that, it means I'm going to need to perform this expansion and try and simplify it. So I'll do it in a number of steps. 4a e to the minus a. We're going to have here, what am I going to expand first? Let's write it how we had it before, which is 4e to the minus a times 1 take a. Okay? There I've just changed the order of multiplication. 4 times that, and then times 1 take a. So that's legitimate. And then the a can even go in here as well. Okay? Like if I distribute the a in there, we're going to have 4e to the minus a times a take a squared. Okay, so that's all okay as well. All right, any questions at this stage? This is probably the trickiest part of this question. Okay, so then let's distribute that to both of these two terms. So we're going to have 4a e to the minus a, take 4a e to the minus a, plus 4a squared e to the minus a. Nice. All right. This and this are going to cancel. What are we left with? C is 4a squared e to the minus a. We've got C, we've got the equation of the tangent. Therefore, what's the tangent? That one there. Okay, so this is a nasty problem, right? But the process is just finding the equation of a tangent. We know how to find the tangent. The complex part here is just there's lots of a's and e's and it just looks nasty. All right, but nonetheless, the process is the same. You've got the point of contact, you get the slope, you find the tangent. Okay, you've even got a direction that you're aiming for. All right. So that's part C. Let's go to part D, unless there's any questions about that. Last question of the exam. Part D, using the equation given in part C, so even if you didn't crack it, you can still use it. Determine the value of A that maximizes the y-intercept of the tangent. What is the y-intercept of the tangent? Okay, this is the tangent, all right? Y equals mx plus c, this is the slope. This is the y-intercept, 4a squared e to the minus a. Okay, so if we want to find the value of a that maximizes it, we should think of this as a function. This is a function, and if you sketch it, it's going to be a curve that has some maximum at some point. And so we're saying, what is this value of a? Okay, this would be a, and this would be the y-intercept. All right, the y-intercept changes depending on the value of a. All right, think about that in the context of the original problem. Here's the original graph. Okay. The y-intercept, all right, is dictated by the x value of the tangent, isn't it? The y-intercept's always changing depending on where the tangent is drawn. And they're saying, what is the value of x, okay, or the value of a in this circumstance, that maximizes the y-intercept? What's going to be the highest y-intercept? All right, so this is the y-intercept equation, and we just need to find the max that occurs there. Let's use some calculus techniques. How do we find when a max occurs? Well, it's when the first derivative equals 0. So we're going to differentiate this with regards to a. How do we differentiate this? We have to use the product rule. We've got one function times another. So we've got u is 4a squared, u dash is 8a, v is e to the minus a, v dash being minus e to the minus a. So I'm differentiating with regards to a, right? We're treating a as we would x. All right, this is going to be 8a e to the minus a. So u dash v plus u v dash. So it's going to be take because it's a negative. Okay. And it occurs when, so how do we use calculus techniques to find a turning point? It's when the first derivative equals 0. All right, looking along there, what's common? Okay, if I'm going to solve that, I'm looking, 4 is a common factor, 4 is a common number. A is common to both, so that can come out the front as well. And so is e to the minus a. And we're left with 2 take a. Alright, so if you expand that, then this is what you'll get. Okay, we'll apply the null factor law. So e to the minus a does not equal 0. A could equal 0. Alright, so from that term, a could 4a times 4a could be 0. Or we have 2 take a is 0, and in this case we get a is 2. Okay, we can reject this solution because we know when the tangent is drawn at 0 here, if you draw a tangent there, well, the y-intercept of the tangent is 0. When x is 0, y is 0 on this function. So therefore, the value of a that maximises the tangent is a. That's all we have to do. Therefore, it occurs at x equals 2. Okay, so what that means is when you draw the tangent at x is 2, the y-intercept is going to be significantly larger than when you draw it at x is 3 or anywhere else along that function. Alright, so nasty last couple of questions. Hopefully follow along all right. So we'll stop there, but I would like to come around and see how everybody's doing, see if there's any sort of common questions.